Nulis
kita menggunakan nomor Romawi terakhir. Kemudian di bab satu pendahuluan kita menggunakan angka 1, 2, 3 sampai seterusnya. Sampai terakhir daftar pustaka. Di sini terlihat bab 1 masih menggunakan angka Romawi, jadi langsung kita ubah aja. Pertama-tama kita ke halaman terakhir yang menggunakan nomor Romawi. Maksudnya terakhir itu adalah foto, jadi aku kalinya di kalimat terakhir. Setelah itu pilih expired, continuous, ada jeda atau spasi, kemudian hapus dan kita klik baris terakhir. Cara membandingkan dan tutorial cara membuat halaman berbeda.
Kelasnya dipakai apa?
Baik, nol. Ah, ini kuadrat nol. Sembilan. Assalamualaikum. Selamat pagi.
Waalaikumsalam warahmatullahi wabarakatuh. Selamat pagi, Prof.
Ya, enggak.
Selamat datang, Prof.
Ya, terima kasih. Saya baru bergabung.
Oke.
Kita masih sambil menunggu yang lain ya, Mbak Eka.
Betul, Prof. Kita insya Allah mulainya 10.35, G.
Oke, ya,
Nah, kasih banyak, Prof.
ya, udah nggak usah panggil saya Prof, itu Pak aja. Ya. Saya belum profesor kok.
Nyari di mana, Mbak?
Assalamualaikum Pak Heri.
Waalaikumsalam warahmatullahi wabarakatuh.
Buku yang itu tahu
Eh,
ini pas
Mas Putut
Saya
ya?
butuh Pak.
Ya. Bagaimana kabarnya Mas Putut?
Alhamdulillah Pak. Saya Pak.
Iya, iya. Saya perlu kirimkan PowerPoint atau saya jalankan sendiri bagaimana enaknya?
Monggo, Prof. Ini baiknya
Saya
gimana?
kirim ke anu aja ya, saya kirim ke chat aja ya, biar yang lain juga bisa mengikuti ya.
Ya, baik.
Oke, sebentar. Oke, sudah saya sediakan di chat. Andai kata nanti pesertanya bertambah, kemudian yang baru gabung belum bisa mengakses atau mengakses file saya, bisa di reposting. Jadi yang baru datang bisa mendapatkan, gitu ya. Mohon maaf, kemarin ada saya diberi background atau enggak ya, atau bebas saja. Saya lupa. Dari Pak Mitra kemarin, enggak ada ternyata. Memang enggak ada ya? Atau karena ini Mbak Eka pakai background gitu. Kalau saya nggak pakai background ya enggak apa-apa.
Oh iya, iya Pak. Saya pakai background. Tapi
Oke,
sepertinya tidak khusus untuk seminar hari ini, Pak. Jadi
oke,
bebas saja.
oke. Ya, siap.
Sepertinya mungkin bisa kita mulai sekarang ya, Pak.
Ya, monggo.
Oke, baik. Bismillah, Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Selamat pagi dan salam sejahtera buat kita semua. Yang terhormat Pak Heri Trilaksana, selaku pembicara kita pada pagi hari ini, Bapak Ibu dosen dan para peserta yang telah meluangkan waktu untuk bergabung dalam sesi seminar BON pada pagi hari ini. Puji syukur kita panjatkan kehadirat Allah Subhanahu wa Ta'ala atas kesehatan dan kesempatan yang telah diberikan sehingga kita semua bisa melaksanakan seminar BON pada pagi hari ini. Saya Eka Wahyuni, perkenankan saya untuk memperkenalkan pembicara kita pada pagi hari ini, yaitu Profesor Heri Trilaksana MSI PhD. Beliau merupakan dosen dari Universitas Erlangga. Beliau menempuh pendidikan master di Institut Teknologi 10 November pada tahun 2005, kemudian melanjutkan studi doktoral di Flinders University di Australia pada tahun 2018. Beliau 5 tahun terakhir fokus risetnya terkait material sains, kemudian sensor, dan juga analisis spektroskopi. Betul begitu nggak, Pak?
Iya, betul sekali.
Baik, hari ini beliau akan memaparkan mengenai topik riset yang tentunya sangat menarik, yaitu mengenai di-titania interface behavior as photonode in DSSC and its spectroscopic investigation. Langsung saja saya persilakan kepada Pak Heri untuk memaparkan materinya. Monggo, Pak.
Baik, terima kasih. Sebentar, saya coba mengatur monitor saya dulu supaya saya nanti kalau mute, unmute, eh, lancar ya. Sebentar. Kalau mute, oke. Baik. Mohon maaf karena saya sekarang sedang berada di ITERA Lampung, jadi kebetulan ada kegiatan International Conference, jadi saya agak skipping ke ruang panitia untuk menjalankan ini, nanti gabung lagi setelah kegiatan ini. Oke, jadi saya sangat sangat mengapresiasi tinggi Universitas Gadjah Mada. Ini prolog dulu ya kan, supaya kita kenal, supaya kita bisa mengambil kemanfaatan lebih banyak, terlebih-lebih mungkin untuk teman-teman mahasiswa atau mungkin dosen muda bisa menjadi motivasi gitu ya, semangat bahwa iklim akademik itu penting. Dan UGM sebagai universitas ternama, terbesar di Indonesia memberikan contoh yang baik. Kita semua yang mungkin berada di luar UGM tentu perlu mengapresiasi dan meniru langkah-langkah baik seperti itu. Kami di Universitas Erlangga juga berusaha melakukan hal yang sama untuk diskusi tiap. Kami biasanya mengambil hari Selasa begitu. Jadi untuk mahasiswa S2, untuk mahasiswa S1 gitu. Jadi kami baru bergulir mungkin 2 tahun terakhir begitu. Jadi seperti biasa, mungkin kami juga akan mengundang beberapa pembicara dari UGM atau adik-adik mahasiswa dari Gajah Mada yang mungkin ingin melatih melakukan sharing communication atau science communication dalam bentuk boleh semacam ini secara online atau datang hadir secara offline supaya lebih dekat. Itu sangat bagus menurut saya. Jadi saya apresiasi tinggi dan saya ucapkan terima kasih. Kalau tidak salah kita ini sudah yang ketiga ini saya diundang. Pertama dulu almarhum Prof. Yasin, saya kemudian Prof. Suryani, dan ini yang ketiga saya. Mungkin nanti dari Universitas Erlangga akan ada pembicara-pembicara lain yang juga aktif berpartisipasi ke rebuannya UGM ini. Dan juga teman-teman UGM juga akan bisa ikut aktif di selasaannya UNER. Kalau tidak salah, ITS itu Senin kalau nggak salah. Jadi ya kita memiliki hari-hari sendiri-sendiri supaya tidak overlap. Baik. Sebentar ini audiensnya. Supaya ini ada langkah yang lebih pushing forward gitu ya. Saya mohon izin untuk menyampaikannya in English ya. Boleh ya mereka ya? Jadi
Boleh,
untuk-
Pak. Monggo, Pak.
Oke. Thank you very much. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
First of all, I would like to say feeling thanks and grateful to Gajah Mada University and all of the participants here, all of the students, lecturers, young staff, and so forth, to gather online here to facilitate what we are going to have as the part of the science communications about what we've done, what we are going to do, and what the potential collaboration that all of the participants here in the Rebon online seminar. So please feel free to ask, feel free to listen up carefully and raise your hands when you got something interesting. Okay, so we are doing as best as we could. All right. So first of all, I would like to introduce myself as the Seminal Program Committee introduced me as I'm the lecturer in Erlangga University as well as the head of the physics department in the Faculty of Science and Technology, Erlangga University. And my name is Heri Trilaksana. And today, what I'm going to talk about is something related to the renewable energy resources. In these terms, we are using titania and dye interface to be investigated as DSSC, stands for as the dye sensitized solar cells. Okay, so dyes attach into the titania. The substrate here is titania, which is solid, and what attached here as the photoactive substance is dye itself. And here we are going to use the dye as the organic components on the basis of HCONS, hydrogen, oxygen, carbon, nitrogen, and sulfur. For some reasons, organic components can be as the very, very championship materials for the dye-sensitized solar cells because a lot of reasons. maybe we can see from the friendly environment and easily to degrade and not toxic and so forth and so forth. This is the first part that I want to explain about the title, what I'm going to talk today. And the second part is about the techniques, how we investigate all of the substance in the di and titania interface, which is about likely it's about chemistry, but I'm not a chemist, so I like to say that it's very, very specifically technical physical spectroscopic investigation. So if we look at some chemists working on the spectroscopic area, they're using FTIR, XRD, EDX, or FEM, AFM, FTM. Some of them are very, very heavily chemist, and some of them are very, very heavily physicist. Okay. In this part, I would like to say the second, but sometimes I still use very, very standard and fundamental spectroscopic techniques, such as FTIR. Okay. I would like to mention about this later on. So this is me, I've already mentioned here, and this is the global issues that motivated me to interact with all of the topics in the harvesting energy from the solar. Okay. I like this picture very much. The big round yellow rounds there is actually the lion's share of the energy coming out from the solar. So if we look through all the numbers here, the quantity is about the terawatts year, okay? So we can do it, start from the tides, which is very green and renewable aspect. It's just 0.3 per year, terawatt per year. So all of the units here is about terawatts, not watts, not gigawatt, but terawatts. And about a bit larger is geothermal, 0.3 to 2 terawatts per year. And then next one is slightly the same between geothermal and hydro. So all of this is the sources that we used for our daily life. So they are from renewable energy and non-renewable energy. So for example, tides is renewable energy, geothermal is still kind of renewable energy because there's abundance and is not quite effectively used. So we had a lot of geothermal resources. Hydro is green technology or renewable energy, biomass is renewable energy, and so forth and so forth. So from geothermal, hydro, biomass, organics, kind of polymer or TEC is green technology or renewable energy, and then wind turbines, natural gas, petroleum, which is quite sensitive issue. And then sometimes we are using the uranium as the fission nuclear reactions to harvest the very, very abundant large energy. And then coal, which is very, very debatable because all of the carbon fingerprints is a big issue, and also the effect because of the mechanism of the greenhouse effect, and then the global crisis in terms of the greenhouse effect as well. So then, if we sum up all of the energy that we used from tides to coal, so that's just less than what the energy that's our Earth got. That's about 16 terawatts per year, terawatt year per year from the sun. It's just from the sun. So if the sun emits 23,000 terawatts per year of energy, and then just 16 terawatts per year that we got from the Earth. So the rest is just coming out of space, spatially. So out of the 16 terawatts, we just use, if you can sum up, 900 in coal plus 300 in uranium plus 240 from the petroleum from 215 and so forth until tides. It's just nothing. Okay, so 16 terawatt per year is very, very uncomparable to what we had so far at the moment. So starting from these motivations, we actually need to explore effectively how the solar energy can be harvested and can be employed by human in around the world. However, this is kind of the organic PV or photovoltaic, which is substance or the device that we can use to harvest the energy, or let's say photon energy, from the sunlight and convert it into the electric potential, which is we can use for our appliance, for our daily life. So nations who are very, very good and independent to other nations without any dependency to the energy resources, they're gonna be very rich. Rich in these terms, not only about the money that you have, about the asset that you have, but about the ability to harvest the energy from the sun. Okay, he's still between pros and contras, but this is quite promising. So on the left-hand side here, we call this the dye-sensitized solar cell. Hang on, I still need to check my, okay, yeah, this is correct. Order one. So the sunlight on the left-hand side here is shining from the left to the right. So the first compartment of the PV organic solar cells is the photoelectrodes. We call this the photoelectrodes because electrodes who is contacting with the photon from the sunlight, from the source of the photon. So on the left-hand side there, they have the photons who absorbed by the material, which is very photoactive materials, and the materials can be in quantum physics or in modern physics. We call that all the ground level electron can be excited into the excitation states, and then they can go further to the conduction bands, go into the other ruthenium, and goes towards the photoelectrons, which is they can be used as the VOC, voltage open circuits, for external loads or the appliance, and then collected back into the counter electrode on the right-hand side. And then the process will be continuing by picking up by the iodine or the liquid to facilitate the electron transport from the counter electrode into the dye. So the forward process in the green arrow there is actually the process that you want to have effectively. And the reverse process on the other way around is the process that we need to suppress or to avoid. So how to tackle the reverse process? This is quite technical, and a lot of paper talking about this. And this is still be potential research since, from my memory, it's around 2004, 2005, until maybe the last 5 or 6 years ago, before they want to tandem to make it together with the polymer. So we will have between dye-sensitized solar cell or dye organic materials with the perovskite. Okay. So in the top right hand side here, this is kind of the aspect. That's why we pick up with the organic photovoltaics. The first reason is maybe they are environmentally friendly, so they're not dangerous, not toxicity to the environment, and they're actually low cost productions. Not very low cost production actually, but they can be very low cost, very cost effectively in comparison to um, the silicon wafer semiconductors. However, the problem is still standing there very clearly. The first one is about their efficiency, how much the photon energy that we can absorb, and how much the potential or electric potential we can produce. And also about the durability, because it just stands for less than 1,000 hours, which is less than 3 or 4 months. So in this regard, this is very still challenging aspect that we need to carry it out. And the appearance is slightly very nice, colorful dyes. If you're using berries, you will see a bit reddish. If you have a bit some different organic materials, it can be greens or yellow or maybe brownies and so forth and so forth. So this colorful organic photovoltaic, and they are very cheap because the substrates you can use either titanium dioxide as what I used in my research, and you can also use the glass titanium indium oxide, tin oxide as the glass materials. So they are very, very cheap and easy to produce. Again, if we compare to the silicon wafer semiconductors that we need, the glass box that we need, the very, very low vacuum, or sorry, high vacuum equipment and very complicated apparatus. So this is slightly the same as the previous slides, but in this picture, we can see like how much is the potential or electric potential between one component to the other, so that we can make sure that all of the photon energy that we absorbed from the sun into the dye as the photoactive materials can be driven into the opposite the opposite electrodes or counter electrodes. So on the right hand side, on the left hand side here is just typically the titanium material or titanium oxide, which is the white color. And the ruthenium dye is slightly a bit red or purple dots there. And then the schematic for the energetic materials is on the right hand side. So this is kind of the most crucial things why we need the titanium dioxide. So the first one, we want to collect the electrons from the iodide into the titanium. Titanium here, because I'm using the ruthenium dye, so I draw here the color of the titanium. Sorry, the dye is in the purple color because ruthenium dye colors is purple. So dye here can be excited into the excitation state because they absorb the photon as h nu there. So this much of the energy is actually need to be above of the the conduction bands of the titanium. Why? Because the electrons from the excited states on the high occupation orbitals need to be transferred into the conduction band. On the right-hand side there, we actually have the iodides, where the diffusion mechanism from the counter electrodes into the iodides to be oxidized into triiodides can be actually transferred from the iodide lowest occupied molecular orbital, LUMO, into the ground state of the dye. So kind of in the left-hand side, there's the output of the electron from the dye. From the right-hand side is the input from the iodides into the dye molecules. And the H nu here is actually the pumping system, how to pump or excited or energized the the electron in the ground state to be excited. Right? So this is kind of like, if we are talking about the pumping system of the water mechanical system, then we have the pump to pump from the ground position, the lowest ones to the highest. All right. So this is a bit similar, but we are not talking about the energetic ones. If we are going here, this is kind of the pathway of the electrons on the basis of the energetic, how much is actually the reduction and oxidation potential. But in this slides, this is kind of the how long, or we call as the how long is the lifetime from each electron's state can be. So first of all, if we pumped the electron from the ground state in highest occupied molecular orbital into the LUMO, so then the electrons can be injected into the into the titanium, but they just have very, very short lifetime on that stage, which is around in picosecond in order. However, the process how the electrons from the titanium highest unoccupied orbitals into the ground state of dye is actually in the order of microsecond or even larger milliseconds. So this kind of wow, it's not very rare, because the comparison between how they can stay there and how they can steal or can be stolen by the dye is actually not comparable. Pico and micro. So then this is that we need to be careful how to make sure that the electrons are not going to be recombined to the dye material to come back to the ground state and recombine there. So we just need to transfer from the excited dye material into titanium as fast as we could, then it's going to be regenerated into the triiodides and going to be in the iodides. From the iodides into the dye material. So if you look through this one, the fastest one is from the lowest ground states dye material to the excited one, which is nanosecond. And then the shortest, the second shortcut is the nanos, and the quickest one is the picosecond, and then the rest is millisecond or either second, and then microsecond and millisecond. So the most quickest one is from the excited dyes into the titanium. We need to make sure that this process need to be very effective and efficient. However, the electrons from the triiodides coming back or recombine to the ground state of the di molecules is about millisecond until second. So more likely, the third one is actually occurred, millisecond to second. And the second most probability is the millisecond to microsecond. And the less is actually nanosecond and picosecond. So this kind of the one that we need to take into account, and when we are doing the research in electrochemical or in a photovoltaics, we need to look at the energetic level very particular. And now I want to introduce some of the organic compounds here. I'm not good in chemistry, to be honest, but we need to look at what actually happening when we are using the organic dyes. Yes, I should mention that the organic dyes is actually, they are very organic. Carbon, oxygen, nitrogen, sulfur. But let me look at the ruthenium there. Why the ruthenium is there? So, as I mentioned before, in the photoactive materials, we need to have something which is very sensitive to be excited due to the photon exposure. So we need ruthenium there. And how to attach ruthenium to all the organic components? Then we are using usually the, I don't know what we call it. I just want to say that's cyclic nitrogen compounds. Okay, what they are could be benzene or whatever, right? So then ruthenium can be attached on the organic components there. And different functional group around on the organic components is quite something that this still can be very interested to be investigated. In my case, I would like to say N719 is the most candidate that we are using on the basis of the organic dyes. I don't want to say that the other is not quite good, but this is just my concerns about N719. The other one is Z907, which is still on the ruthenium, but they don't have any COOTBA. And this is just predicted they can facilitate all the charge transfer more effectively than the other. So theoretically, in calculations, N719 can facilitate the charge transfer more efficient rather than the Z907. And the other one, we used also very pure organic compounds. We call this L0. Why L0? I don't know. I don't know, because they just manufacture it and we just need to investigate. But if we look at to the chemical organic compounds here, nitrogen as the central atoms, and then benzene is around on the three ligands, and then C and carboxylate, COOH. However, on the right-hand side, we are using L0Br instead of just L0. What the purpose behind this is just because we need to have the heavier material rather than just HOCNS. So organic component is awesome. They're generous, they're fantastic, but they're just very light. For some reason, we still have something heavier than them. So bromide is the one that we are using there. I will tell you a bit later about this. The other one is about PD2 and LEG1 as well. If you look through them, they are fully 100% just organics without any bromide, without any other heavier atoms. So then it's very challenging, okay? And on the right-hand side there, again, I'm working on the N719, but I combine with the CDCA. If I'm not mistaken, it stands for cyanodeoxycholic acid. What is that? Please don't ask me. I don't know at all about that. But the function of the CDCA in chemical agglomeration mechanism, they can reduce the surface passivation. They can reduce the surface activation, or they can facilitate the surface passivation. Okay, we are going to implement the CDCA into this N719, how to attach into the titanium substrate, and how they will be structured. Now we move to the techniques. All of these are about the spectroscopy. Nikis end up with the S, IPS end up with the S, MES, UPS, XPS. So all of them are spectroscopic. IP spectroscopic, Nikis spectroscopic, MES spectroscopic, UP spectroscopic, XP spectroscopic. So we're gonna use the spectroscopic thing or techniques to investigate how the electron is actually behaving around the circle, the cyclic. So on very basic drawn here, sample preparation in UHV means that our samples need to be in high vacuum containers or chambers. We call this ultra high vacuum, UHV. Why? Because we are going to emit the electrons. If we are going to emit the electrons, mean the mean free part of the environment need to be larger than the mean free part of the electron. Otherwise, the electrons are not going to be ejected from the metal surface bonding, so energy bonding. We already know about the work functions. We already know about the photoelectric concepts. So the electrons are not going to be overcome all of those hurdle or barrier. Otherwise, we need to have the ultra high vacuum. So, and then while the system is already perturbed by the high energy, then the electron will be emitted. The ejections is actually very, very crucial because we are going to have the information from our sample by investigating and confirming what is what about the electron energy. And the spectra is going to be on the bottom of that picture. So this kind of the Nikis. So I would like to go back. This Nikis one, the top one there. So IPS is not very standard. MES and UPS, they are standard. XPS is standard, but IPS and Nikis is not very common, but convenient for the electronic spectrum. Electron spectroscopy or ion spectroscopy. So this is what we will do in Nikis. So basically, there are two parts of the beams, which is the ion beams and the neutralized ion beams. So we want to have the target on the right-hand side. So just please ignore the arrow showing how much the degree is, how much the sample is going to be tilted. But the targets at the basic of this structure is on the right-hand side. And the source of the helium ions is on the bottom, a bit slightly up there. And then they will be bombarded into the target, and they will be interacted with the target. And the ions, I want to say that's ion. Ion is the atoms who's losing some electrons. And then while they're interacting with the target, and the target has a lot of or source of the electrons, they just steal the electron from the target to produce the neutral helium. So helium ions exposed into the target and they will be scattered back by producing the neutral helium. So the target need to be less electron after the scattered back of the helium. And then the helium goes through the left and then collected by the channel plates. On the channel plates, they will be confirmed that how much is the electron, how much is the energy of each of neutralized helium, and then as a function of the all of a pathway here, then we will see the concentration depth profiling of the targets. If you are looking at the dye molecule, so the dye molecule on the substrate need to be as a target. And the helium ions cannot to be produced by the ion guns in the range of the kinetic energy around 1.5 to 5 kilo electron volt. Oh, that's not much. Yes. Because if you have abundance as larger helium ions energy than this, then we actually have the Rutherford backscattering experiments, or even larger than that. Okay, so this kind of the setup of the Rutherford backscattering experiments to implant all of the solid materials in terms of the high energy ions bombardments, but this one is very surface sensitive, very surface sensitive. The question is how to bombard all of the helium ion into the targets precisely. Then we will see the electrostatic deflections. Like we need to drive a bit tilt to the left, tilt to the right, because we need to make sure that all of the ions can be adapted with the surroundings, because the surrounding is actually a lot of potential, and by Coulombic interactions, they can be deflected very easily. To protect the ion to be deflected on the way that we are not going to have, so then we need to operate some potential in the channel tron of the UV and UX. UY and UX. Okay, in the corresponding of direction in X and Y. So then the helium ion can be targeted into the targets very precisely. So electrostatic deflections is kind of the things that we need to understand, but that's still interesting. If we look through the oscilloscope in very conventional way that all of the beam can be spotted into the center, that's why we need to apply specific voltage between the channel trons, between two positive and negative metals. So then the electrostatic there can affect the ions or the electrons in the oscilloscope targeted in the center point of your screen. So this is the similar concept of that. But the target is not the screen. The target is your ruthenium and titanium. Okay. So this is just the text to reduce the schematic that I am very happy to explain about the dyes, the spectroscopic techniques, and so forth. So first, we are using the XPS. So it stands for X-ray photoelectron spectroscopy. So photoelectron means that electrons can be ejected by photo interactions. And the photo here we are using from the X-ray. So X-ray range of energy interact with the substance, with the materials, then the materials can be excited, or maybe more than that. The electron can overcome the work functions and they can be emitted or ejected from the metals. And then they will be scattered and we need to collect there into the hemispherical sensors. On the right-hand side here, we will have the electron energy analyzers. in hemispherical form here. So all of the electrons scattered from the sample need to be collected on this. So by doing so, we will have the spectra as a function of the energy or binding energy, and could be kinetic energy of each electrons from where they are coming from, and they are very unique and very specific, corresponding to where they are ejected from. If they are ejected from the carbons, they will be emitted and appears on the numbers of the binding energy on that much. If they're coming from the oxygens, then they will be appears on the binding energy on that much, or kinetic energy on that much. So you can pick up with which one you would like to use. The second one is about UPS, ultraviolet photoelectron spectroscopy, which is they are very similar with the XPS. However, we are not going to use the photon from the X-ray. So we just use from the UV, ultraviolet. Hang on, give me a second. I have a call. So sorry, just a second. Okay, just continue. So we just have the ultraviolet. Hang on, give me a second. How much time do I need to have? I think I still have from my timing here is just 5 minutes left, or 15 minutes left, because we started at 10:35, right?
Yeah.
Just remind me if there's we ran out of time, okay? All right. Ultraviolet photoelectron spectroscopy. Here we are using the ultraviolet instead of the X-ray photon energy. So that's the purpose of we are using it, because in the XPS we can see all of the electronic structure from LUMO, from the core level of energy to the highest unoccupied. But in the UPS, we just want to show that this very sensitive to investigate between HOMO and LUMO energy level. And the third one is meta-induced electron spectroscopy, which is the more thorough techniques to the surface investigations, or at least, let's say, the interface as well. And in the meta-induced electron spectroscopy, we are not going to use the energy from the X-ray, the photon energy of the UV. Basically, we are not going to use the photon energy. So we just to interact between the ions to the topmost of the atom that we have on the samples. So the helium just go around the surface. We blow the helium ions to interact with the topmost atoms, and the electrons will be collected. And we want to say that the electron lose couples of energy. So the electron is blown on the surface and then scattered, not scattered, because they are not elastic or non-elastic scattering mechanism, but they just slowly and slightly interacted with the surface and then collected back by the detector and measured how much the losing energy they had. Okay, so they're very surface sensitive. And the last one is NICUS. From the acronyms, they stands for neutral impact collisions ion scattering spectroscopy. So the basic idea is the scattering. The scattering by what? By the collisions. The collision with what? The collision with the ions. What ion they're using? We use the helium ions. And then what kind of the collision? They need to be impact collisions. And what is the result after this mechanism? The ion will be neutralized. So we call it as neutralized impact collisions of helium-ion scattering spectroscopy. That's the thing. But we are not limited by the helium only. We can use the argon, we can use the inert gas particles. Why? Because inert is quite stable. Okay, then why we end up with the helium? Helium is the lightest one, not the lightest one. The hydrogen is the lightest one, but the handling with the hydrogen is a lot tricky. So let's use with the second, the lightest one, which is helium. If we are interacting with the metal, which is very stable, very robust, we can still use the argon or even xenon, but it's quite rare. Usually we can use between argons and helium. I haven't had any experience with the argons. First of all, argon is more expensive than the helium. Okay. This looks very similar to the Rutherford backscattering, as I mentioned before, and they use just lower energy instead of the highest energy as what Rutherford backscattered had. Next one is, oh, it's not working. What happens? Stop. All right, so this is photoelectron spectroscopy. As I mentioned before, this is just the schematic, how the electron can be collected from the surface. If we look through the samples, we will see the angles theta there as the takeoff angle of the electron. So kind of the electron is actually ejected from the samples, from your samples, silicon oxide here maybe, or silicon plains, pristine silicon without any oxidations. Then the electron ejected on the specific directions towards the electron collection lens. So there's a lens which is collected the electrons. And first of all, I just imagine like the optical lens working together as the structure of the alignment between one to another, but this is not actually how it works. The electron lens here is actually kind of the channeltrons, similar like the pi plates A and B with the potential between them, and then they can be directed into three-dimensional direction, so X, Y, and Z. So then when the electron is not actually at the certain or specific direction, then they will be redirected into the hemispherical. So then we will see that all of the pathway from the electrons is going to be in this circle in various radius. So the more radius we have, then the less, the more radius we have and the more energy they have. Means the electron has a larger momentum. Larger momentum means they have a more velocity. So the faster is going to be the more radius they produce. The less radius they produce is correspond to electron with the less energy emitted from the sun. So the question is why the electron kind of have the different energy when they emitted from the surface? It's very easy to answer because the barrier are different. Sometimes if they are bounded to some metal, which is the working function is very high, then let's say the electron will be very exhausted to overcome the work function. And then when they eject it, they have less electron. They're very big. Okay, they are emitted, but they are emitted in the weak conditions. However, if they are very, very in the surface and the work function is very, very low because they attach into some materials with the low work function, when the photon is absorbed, then it can easily to be ejected, and they will be ejected in their very fast velocity or in high momentum. So they produce in very different positions, or we call this as channeltron. So in the purpose of this spectra here, if you look at on the right bottom there, so there are couples of a peak and then the bumps and the valley and the through and crest. The sum of the picture correspond to the number of the electron they collected and in which energy they are coming from. So on the x directions, they are actually as a function of the binding energy or the kinetic energy. And the y direction there is actually the number of the electrons. So the higher the spectra, the more electrons is produced. So before we continue with this experiment, usually we need to double check whether the spectra produced is correct or incorrect. Otherwise, we will spend a lot of time, and at the end of the day, we just collect rubbish because the spectra we collected is actually not coming from that specific targets that we are going to have, but because all of the setup is not in the proper structure and not well alignment, so then the spectra doesn't mean or doesn't reflect anything. Okay, so we need to be careful. The more important thing is the alignment of the electrons scattered from the sample to the channeltrons. And the second one, we need to look at in which sensitive that we are going to measure. If we implement more energy, more than 1.5 kilovolts, then the more photon energy is coming, and then the more electron is ejected. So then the spectra is very high, which is we can't distinguish between which one is crest, which one is high, which one is bump, which one is peak, and so forth and so on. We call that the sensitivity is that works. Oh, sorry, why I can't move? Okay. This is kind of the equipment by courtesy of Professor Gunther Anderson in Flinders University, South Australia, my former supervisor when I'm doing PhDs, and also still my collaborator so far until now. And then the binding energy equals to photon kinetic energy. This is kind of the equation that I mentioned about the work functions. So we need to overcome the work function before the electron is ejected. And the next one is the main chamber that I need to introduce my samples. There, the round center there is the main path of the ultra high vacuums, and the tube with the high voltage sign there is actually the X-ray sources. And then the rest is just the detector, the hemispherical, and so forth. And all of this need to be driven by the very high, ultra high vacuum pump, because we need to pump it down until 10 minus 10 millibars. So, just ignore this, my picture there. Okay. So that's on the left-hand side here, we will see that the work functions pi there is actually the photons energy take the difference of the Fermi level takes by the cutoff energy. So what is cutoff energy? I don't want to say in these slides because the slide is a bit in the vertical picture. I would like to say in these slides. So if you look at the on-site, the cutoff there, so we will see there's the nothing, and then there's a spectra very high, and then goes down, we will the crest, and then go up to the pump, and then go down, up again, down, and nothing. Okay, so we will see between the onset energy cutoff to the end right hand side there. This called as the HOMO level. So in the electronic structure, we are working with the HOMO level here. So HOMO level here is when the electron is going to be nothing. So the last spectra on the right hand side here, it's around maybe 1, 2, 3, less than 3 electron volt of bonding energy. They are the topmost electrons that can be ejected, the weakest one, I want to say. But the top left hand side here, this kind of more than 17 or 18 electron volts, this is kind of the most, sorry, on the other way around, the less electron volt is the deepest one, which is around 2 or 3, and the 18 one is around the topmost electron one, which is very easily to be ejected. And the miss one here, so I will say this is 34, so I will be very quick. So this one is helium on the left-hand side and interact with some functional group or atoms here, and then they will be scattered back as the ion. So not the S ion, the electrons there, and then the electron is collected. So then, if you look at the left-hand side here, the helium produced the electron from the unwell structure of the functional groups. The green one is the topmost electron, and the functional group is the red and the black one. On the right hand side here is the other substance, which is very, very well defined. The direction is very homogeneous. So then when the helium ions coming and interacting with them, so the electron is ejected in this very specific and well defined. So we just have the spectrum on the left, and we will have the spectrum on the right. Depends on how the spectra, how the structure of the topmost electron here. So the more regular one, the cleaner the spectra. The more unregular, on the other case, the more complex they are going to be. So the sum of the species 1, 2, 3, and so forth will be produced in the purple, or what color is the top one here. So if it's possible for us, we will arrange all of the substance as on the right hand side. But yes, we believe that it's hard to arrange all of the topmost electrons, topmost atom in a very regular order. And the last one is about Nikes, which is very, very sensitive to the concentration depth profiles. So if we go back to the Mies techniques here, they are very surface sensitive. So to investigate the topmost layers, but this one is to go a bit down in the depth concentration profiles to look at which one is which, a bit more surface position and a bit deeper positions. So if you look at the dots here, there are two colors, red and greens. If we look very, very roughly in the estimation of what we can see here, red is a bit more going to be to the surface rather than the greens. The red is still on the deepest one, but the green is more likely there on the deeper one, less on the top surface. So if we look at to the helium here, the helium ion is coming and interacting with all of the substance here, all of the particles here, and then scattered back as the helium neutralized helium. Then they will be interacting with the green and red. And as we can see here, the more they're interacting with the red, the less intensity they will be. And the number of the electron of interacting with the greens, and the more they are going to be as the dip going to be higher. It means that the green one is going a bit more deeper rather than the red one, because the red one is more likely they are less than 5 or 6 angstrom. They are very high occupation there. But the green one, they less than 5, but they are more in the depth of more than 7 angstrom. So this is very when I used and understand about this concept, wow. In undergraduates, we learned about the Rutherford backscattering as the investigation how the models of atoms in J.J. Thomson's and Rutherford and Niels Bohr and so forth. And then we understand that the room behind the nucleus and the electron is actually more dominantly by the vacuum. Okay. And in the center of the atom, they're actually the massive particle, which is protons and neutrons. So then this concept can be investigated or can be employed to determine in which depth the target is located. And on the basis of this Rutherford backscattering, just we need to reduce the energy. Instead of doing with the heavier elements, we just use the helium ions, then we can have the techniques how to investigate very sensitive and very precise of the depth profiling as a function of the depth. So this is the equipment. And then this is the IPS, which is inverse photoelectron spectroscopy. So we need to do this as well because usually we can determine the work functions if we already know the material database. But if we don't have what is the characteristic of the data of the materials, then we need to double check with the IPS, inverse photoelectron spectroscopy. Inverse means that we are not going to collect the electron or ejected electrons from the photons perturbations, but we need to flip on the other way around. We perturb the system by the electrons, and then the electrons will occupy the lowest or the metastable, and then they can go to the stable position or to the ground state by emissions, emits the photons, and then we detect the photon energy. So we will see how much is the electrons. So this is kind of similar to the photoelectron spectroscopy, disturbing the system, perturb the system by the photon. We investigate the electron, but on the other way around, we perturb the system by hitting the electron, transfer the momentum, and then emit the photons. Then we investigate the photons. So IPS can be double checked the work function and homo-lumo level electronically. So these are all the findings. I'm working on the organic substance in the technique of XPS, UPS, MIS, NICIS. And then the kind of the results on the MIS, on the UPS. And then this is on the MIS. If you can see here, the red one is the L0BR. And the blue one is the titania, the pristine titania without any organic material, any dye material. So with dye materials, we can see there's the bump, little bump here, the red one in front of the very big spectra here as evidence that's okay, L0BR is there. So how deep they are, then we just plot from the energy profiling, then we will see this. On the right-hand side, the concentration as a depth profiling can be investigated. So this is kind of the publications. This is still on the way on, oh, hang on, PD and LG2 is already published. And this one is already published. This one is the first publication I had. And that one is the same, still the same data. That one restructuring in 2018. And this kind of the conclusions about the iodines forming the dipole layer. I don't want to say that, but I want to talk about dipole layer here. The organic dyes with the bromide can be investigated as the as the spy atoms. So the bromide is the spy atom because the NICIS need to have something heavier than helium. So helium need to be scattered by something. heavier than helium. If we are using nitrogen, oxygen, sulfur, carbons, yes, they still have, if I look back to this spectra. So the blue and right is actually can have the little bump. Okay, the first bump is about carbon. The second bump is about nitrogen. The third one is about oxygen, and the front one, the red one, the little bump at the front, they must be the bromide. The bromide as the representative of L0PR di molecules. So I think that's all for my talk today. And thank you for listening. The rest of time I can offer to Mbak Eka or Mas Putut. Thank you very much.
Baik, terima kasih banyak Pak Heri atas pemaparan materi yang sangat menambah wawasan dan komprehensif, tentunya membahas mengenai bagaimana kompleksitas dari dai dan juga titania dalam aplikasi DSSC. Oke, selanjutnya saya persilakan kepada Bapak Ibu yang ada di room Zoom. Jika ada yang ingin ditanyakan, boleh menuliskan di kolom chat ataupun menggunakan fitur raise hand. Silakan. Oke, baik. Mungkin saya ingin mengajukan pertanyaan, Pak. Saya lihat tadi beberapa metode ya yang digunakan dalam menganalisa menganalisa dari proses pembuatan dainya dan juga titaniumnya. Nah, yang ingin saya tanyakan Pak, bagaimana pengembangannya ke depan untuk mengarah ke percepatan pengembangan DSS ini, karena melihat tentu banyak tantangan begitu ya Pak yang dihadapi, apalagi berkaitan dengan pengembangan yang diharapkan lebih cepat dari DSSC ini. Seperti itu, Pak.
Okay, that's a good question. Ya, jadi bentar, saya menuliskan ini. Lupa. Oke. Ya, jadi memang kendala dari DSSC ini adalah, saya sedikit cerita ke bagaimana struggle-nya si Michael Gratzel ya, bagi orang-orang yang berbicara tentang organic photovoltaic ya. Diawali tahun 92 itu secara mengejutkan Michael Gratzel itu bisa menunjukkan bahwa material dye yang dari berries, dari anggur ya, dari buah-buahan itu bisa sampai pada efisiensi dalam pemanenan cahaya matahari menjadi listrik itu 12%. 12,3 dari yang sebelumnya hanya 6 atau 6, nggak sampai 7. Ini kan semacam lompatan. Tahun 2005-2006 hal ini sangat-sangat mengejutkan. Kemudian dikaji terus sampai 2009, kemudian stuck. Stuck itu artinya tidak berkembang lagi efisiensinya ya. Sehingga researcher itu menjadi desperate. Kita kalau melihat begitu kan, ini bagi teman-teman, bagi adik-adik mahasiswa yang ingin melakukan trace terhadap progres sebuah topik, itu kan kita bisa melihat dari jumlah number of articles ya about that topic. Kalau misalnya dia masih trennya banyak yang meneliti, dia pasti naik. Citation-nya pasti naik gitu kan. Tapi kalau Anda sudah lihat dyes and solar cells, setelah 2011 itu dia turun. Ya. Dyes and solar cell ini turun gitu. Diganti number of publication, number of article, number of citation itu naik di perovskite gitu kan. Jadi sekarang kalau kita bertanya bagaimana dyes and solar cell, masih ada orang yang meneliti tentang kegunaan atau bagaimana memaksimalkan functional materials gitu ya dari organic dyes itu masih ada yang pure di SSC termasuk saya gitu kan. Akan tetapi orang yang melihat potensi selanjutnya itu ada yang sudah sampai di atas 12 dengan menandemkan dengan perovskite gitu kan. Nah, jadi kalau kita bicara, Pak, bagaimana, Pak? Ini nanti nasib material dye ini bagaimana? Ya, bagi orang yang masih berbendera dye, sensitize, solar cell, gitu kan, itu ya tetap akan melakukan dengan fully organic compounds, gitu kan. Tapi kalau yang perovskite, dia sudah mulai mencampur-campurkan dengan polimer lah, mentandem-tandemkan dengan yang lain. Gitu, itu yang dilakukan oleh orang. Dan awalnya memang promising juga itu PV itu, perovskite itu. Tapi sekarang yang terakhir itu juga sudah cukup banyak, cukup optimis orang-orang itu ya. Sekarang bahkan banyak sekali peneliti-peneliti yang sudah mulai nekat ya. Saya nggak tahu nekat atau desperate gitu ya. Tapi intinya sudahlah, berapapun yang namanya efisiensi itu nggak penting bagi dye sensitized solar cell. Kenapa? Karena sunlight is abundance gitu loh. Sunlight itu 23.000 terawatt gitu. Yang diserap oleh bumi saja 16 terawatt year terawatt year per tahun gitu. Lalu ngapain sih kita meningkatkan efisiensi gitu? Walaupun efisiensinya 1% mah nggak apa-apa gitu kan. Yang penting kan sunlight-nya banyak. Itu pemikiran orang optimis tentang harvesting dari sunlight. Tapi permasalahannya tadi kan tidak hanya harvestingnya berapa persen, durability-nya juga cepat rusak gitu kan. 4 bulan aja sudah corrode gitu, sudah volatile, sudah rusak, nggak bisa emit eksitasi lagi gitu. Ya berarti kan harus diganti, walaupun toh menggantinya juga mudah gitu. Tapi kan masa iya kita punya genteng yang terbuat dari dye sensor solar cell 4 bulan ganti genteng gitu kan nggak mungkin gitu. Nah sekarang orang photovoltaic, organic photovoltaic itu sudah mencoba membuat material-material yang painted gitu loh. Jadi tidak printed lagi tapi painted gitu, dikuaskan gitu kayak ngecat gitu kan. Saya juga nggak tahu itu nanti anode dan katodnya campur atau gimana atau lengket atau nggak tahu gitu. Tapi mereka memang sudah punya informasi bagaimana fungsional materialnya itu bisa menjaga ini foto foto itu foto atau ini counter electrode gitu kan di antaranya ada material itu dan dia bisa melakukan fotosensitasi gitu kan. Jadi daun lah gitu ya, daun tapi hasilnya bukan gula tapi hasilnya adalah uh, tekanan listrik gitu. Kurang lebih seperti itu Mbak Eka. Jadi ya saya menjawab dari tren yang ada saat ini.
Ya.
Silakan.
Baik, terima kasih banyak Pak. Berarti di sini sebenarnya yang paling penting itu untuk pengembangan selanjutnya mungkin di bagian dye-nya ya Pak. Dye-nya jadi
Betul.
ya
Ya,
karena saya lihat mungkin dye-nya ini kan yang menyerap energinya ya Pak, energinya.
ya
Jadi
dari foton.
ya. Jadi itu yang sangat berpengaruh terhadap efisiensi dari DSSC-nya.
Sebetulnya tidak juga karena elektrolyte-nya juga memberikan kontribusi tadi. Hanya karena elektrolyte itu waktu hidupnya, lifetime-nya tadi millisecond sampai second gitu kan. Artinya memodifikasi elektrolyte itu lebih sulit. Sedangkan dye itu tadi kan picosecond. Jadi memodifikasi dye itu lebih signifikan gitu loh daripada bukan berarti itu satu-satunya, tetapi the most promising gitu lah ya. Ya.
Baik, terima kasih Pak Heri atas jawabannya, atas pemaparan materi yang telah disampaikan. Tentunya ini adalah topik yang sangat menarik dan butuh pengembangan lebih lanjut ke depannya. Karena tentunya ini akan memberikan manfaat yang baik juga dalam dunia riset, karena mengingat energi matahari itu menyumbang energi terbesar begitu untuk dimanfaatkan dan itu gratis, jadi bisa dimanfaatkan untuk penelitian. Nah,
Ya.
karena waktunya sudah hampir selesai, mungkin saya mengingatkan kepada teman-teman yang ada di room untuk mengisi link absensinya, karena nanti sertifikatnya akan dikirim melalui email yang diisi di link tersebut. Mungkin masih ada yang ingin mengajukan pertanyaan. Silakan.
Saya biasanya begini kalau ke mahasiswa saya itu, there is no silly questions gitu ya. Supaya apa? Supaya satu mereka berani, dua kita itu sebetulnya bisa bagus, bisa punya capaian, punya kemajuan itu bukan dari sesuatu yang besar ternyata. Kita bisa maju, kita bisa punya satu capaian tertentu itu dari sesuatu yang kecil. Dan sesuatu yang kecil itu biasanya diawali dari kemauan, kalau nggak mau keberanian ya, tapi kemauan untuk raising hand atau bertanya. Oleh karena itu resepnya yang harus dibangun oleh adik-adik mahasiswa yang ingin belajar lebih jauh tentang apapun ya, tidak harus tentang dunia riset, tentang pengembangan diri, tentang yang lain. Yakinkan pada diri kita bahwa there is no silly questions. Tidak ada kok pertanyaan yang sangat bodoh atau sangat ya memalukan, itu nggak ada gitu. Justru yang memalukan itu kita nggak ngerti, nggak mau tanya, itu kan yang memalukan itu kan. Memalukan bagi diri kita sendiri. Orang lain sih nggak tahu, tapi diri kita sendiri yang tahu gitu. Oke, silakan. Kalau masih ada yang ingin bertanya. Contoh sederhana, tanya aja misalnya, Pak, itu kan complicated equipment itu ya Pak ya. Itu adanya di Flinders University gitu. Saya kan orang Indonesia Pak, hidup aja susah gitu kan. Biasa aja kadang-kadang, beasiswa aja kadang-kadang dapat, kadang-kadang enggak. Kiriman kadang-kadang telat gitu kan. Gimana ceritanya? Nah, stop asking this question gitu kan. Jadi kalau memang ada sampel yang ingin diteliti atau dilihat tentang bagaimana interface-nya atau bagaimana sensitivitas surface-nya terhadap apapun lah misalnya. Jadi lab tempat saya sekolah itu dulu tidak hanya untuk fotovoltaik saja gitu kan. Tentang apapun yang sifatnya itu surface sensitive, mereka terima gitu kan. Jadi misalnya ada saya meneliti tentang efisiensi dari bahan alam ini saya nyebutkannya aja nggak bisa bahan alam itu apalah misalnya kitosan terhadap gitulah apa terhadap terhadapnya kan substrate tentunya tuh. Nah ini seberapa efektif ya? Oh, hasilnya in vitronya efektif, Pak, gitu gini. Nah, ya kamu bilang efektif-efektif untuk bakteria, untuk in vitro ini, uji ini oke gitu loh. Tapi scientifically kalau kamu mau menguji itu biasanya spektroskopi harus mengatakan hal yang sejalan dengan ceritamu gitu loh. Jangan ngarang seenak udelmu, oh ini baik, ini untuk membunuh bakteria. Iya, 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 wis ngerti. Tapi mikromekanismenya itu spektroskopik yang harus memberikan judgment gitu loh. Itu yang ideal sih kalau saya melihat di kuartil-kuartil tinggi dari jurnal itu double check dari beberapa sisi itu memang sangat-sangat penting gitu. Nah misalnya ada yang bertanya, Pak ini saya punya sampel nih udah saya dapat nih, tapi saya nggak tahu surface sensitifnya kayak apa gitu. Concentration depth profilingnya dia akan absorb sampai level di mana itu saya nggak tahu Pak. Udah kirim aja ke sana gitu kan. Pak, saya boleh ngirim ke Flinders? Boleh gitu kan. Justru nanti ketika dapat hasil, publishnya bisa bareng kan sama beliau-beliau itu kan. Kenal kagak, ke Australia nggak pernah, tapi publicationnya ada gitu loh. Jadi nggak perlu dah, tolong diubah itu mentalitasnya itu. Lebih baik saya ke luar negeri gitu kan. Bisa foto di Petronas gitu kan. Enggak, yang bikin hebat bukan itu. Yang bikin hebat nama Anda di co-authorship dalam sebuah artikel. Nah itu bagi mereka yang pengen jadi akademisi. Itu ya, dari researcher. Ya mudah-mudahan masa depannya nanti bisa lebih cerah, lebih termotivasi, lebih terjaga lah ya motivasi. Saya ngomong gini nggak cuman ke forum ini toh, ke semuanya saya juga ngomong gini. Saya juga pengen gitu ya. Indonesia itu generasi mudanya kayak Mbak Eka, Mas Putu dan yang lain-lain ini ke depan nanti betul-betul bisa eksis gitu ya, mengangkat. Ini kan sekarang kabinet baru sudah ada nih namanya Kabinet Science and Technology gitu kan. Di Instagram sudah ngomong banyak, wah we will improve. Oke, let us see. Saya bilang gitu aja udah. Oke, terima kasih Mbak Eka. Monggo.
Ya. Terima kasih banyak Pak Heri atas insight-insightnya yang sangat menambah semangat kami para peneliti-peneliti muda. Semoga bisa sesukses Pak Heri ke depannya.
Amin, amin. Lebih sukses dari Pak Heri gitu yang lebih tepat.
Ya, amin. Ya,
Ya.
karena waktunya mungkin sudah cukup, Pak, jadi mungkin Pak Heri juga mau melanjutkan kegiatan konferensi di ITERA. Terima kasih banyak Pak sudah
Ya.
menyempatkan waktu untuk mengisi seminar Rebon pada hari ini. Terima kasih.
Sama-sama Mbak Eka dan terima kasih juga untuk semua. Saya akhiri, Assalamualaikum warahmatullahi taala wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Saya izin live nggih.
Oke, makasih banyak Pak.
Sama.
Untuk teman-teman yang masih di room, jangan lupa untuk mengisi presensi yang ada di kolom chat. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.